Okay, so welcome back. Seems that some already went to the pub. Okay, so we start the afternoon session, which will be a little bit strange in the sense that will be no breaking between session 3 and session 4. Okay, so we have in the session 3 4 talks, more or less loosely related around the materials modeling and software development for that. So we start with Harvey Devereux. Harvey comes from London and will tell us about his tribulations and successes that he had implementing on-the-fly analysis in DL Poly.
Okay, thank you, Alan. Right, so yeah, I'm going to talk about some work we've been doing on calculating system properties on the fly in DL Poly. This work I've been doing as part of a postdoc, but also at Queen Mary, but also closely working with Alan and Ilian at the Dahlsbury Lab. So what am I going to cover? Well, first off, I'll give a brief overview of what DL Poly is, and then I'll move on to talking about on-the-fly correlations, which is going to be our vehicle to on-the-fly analysis. And in particular, I'll start off by gently introducing a big picture of it, then go into some theory, the design of our software and what our approaches were and how it works for a user, and then conclude with some case studies and obviously the conclusions. Right, so DL Poly is a classical molecular dynamics code. It's been in development for a number of decades now, since the 90s at least. It's written in Fortran and is currently open source on GitLab. You can follow these QR codes if you're interested. And as part of the project, there's also this Python meta package where you can write your workflows for what you want to do with your molecular dynamics with DL Poly as well. So some current developments. So obviously there's this on-the-fly correlation functions I'm going to talk about today. And there's a few other projects that are in the works or going to start at some point, I'm sure, including GPU acceleration, but also things such as data provenance, possibly using AIDA, as we heard about in the last session, but also integration with, for example, another Python meta package called the ASC, and of course there's our Python meta package as well. So moving on to the big picture of what I'm talking about. Analysis can be done by collecting the system trajectory of your atoms, molecules, whatever you're working with, compiling that into some big database, say the trajectory file X, and then processing it with some algorithm. This can be done, but of course can create infeasible storage space requirements. So you could be dealing with gigabytes, terabytes, or even petabytes of data, for example, which on HPCs you can work through that amount of data, but still it does introduce input-output penalties during runtime, and then whatever algorithm you make or some other software you have to then run on the data set, can also introduce essentially runtime penalties in your entire workflow as well. So what I mean by on the fly is this cartoon here, where instead of producing the series of data points, these X, and then compiling it to a data set and computing some, passing some algorithm over it, we recast the algorithm to work on the data as it's generated, obviously in this case within DL Poly, which would save runtime, for example, through not storing the trajectory at all potentially, and produce hopefully the same analysis, which is what we'll come on to at later parts of this talk. So just some brief context on this as a general point when it comes to on-the-fly analysis. I suppose the context in the literature generally is you want to look at online algorithms or streaming algorithms. Slight difference between the two being that streaming algorithms, you don't necessarily have an endpoint to your data. You could think of like a windowed algorithm where you're constantly reviewing a stream of data that's being generated and still wanting to get some kind of analysis done on the fly. So to start moving more into the specifics, a quite nice example is the running average, because it is an online algorithm, but it's also very simple. We can obviously compute an average over n data points. We can also compute an average over n+1 data points. And based on these two formulas, we can create a recurrence relation, which allows us to get the next average given a new data point. And so that means we don't have to save any of the previous data at all. We can just throw them out or not save them. And this is obviously used in various contexts, molecular dynamics being one of them, and is quite a nice example of what we're doing. But just as a slight caveat here, so if you do the same thing with a variance, you can find there is, depending on the way you write down your algorithm, you can get either an increasing error with the amount of data you have, or something that levels off at a value. The point of this being is that how you take your offline algorithm and structure it as an online one can have implications in terms of the error of your result or other things. And fundamentally, that comes down to the fact that there are different computations going on, different things are multiplied or added or whatever. So as kind of an overview of the broad ideas, what we want to do is we want to go from this cartoon where we take the data into some data set and then compute something to a workflow where we compute it as we go. And in this case, we're going to be looking at correlation functions of this form. In particular, so we have two observables, X and Y, which are time valued. For example, they can have some dimension, and we want to be able to compute a correlation between these two observables. So how we do that, in fact, this is a problem which is, well, being solved in various ways, but one in particular is called the multi-tau correlator, which has a history in physical experiments as a hardware device, all the way through Franklin Smith in 2000s with a similar algorithm towards this paper here, 8, which talks about the multi-tau correlator itself. And the broad idea is essentially the same in these various contexts, is that you have your data coming in. So, for example, think of it as a particle's velocity or something like that. You collect it in a data structure, which is a hierarchical data structure, where the relation between the first and the second level is an averaging. So you're essentially coarse graining your velocity or whatever it is your observable is over the simulation time, and storing it in this block hierarchy. And the reason why that's useful is when you have a new measurement of the observable, you can use this block hierarchy to work out the correlation, or the new correlation at the new lag point quite efficiently by not, you don't have to recompute everything. You can just use this structure. So just as a schematic of what's going on, so you have your signal, which is the data here. This is then averaged down, in this case, over 3 temporal values into another block, which is then further averaged as the data comes in. And what this essentially means is you have this relation here with T is IL to the M, where M is your averaging parameter of T being your lag times in your correlation. But this is all algorithmic details. So what does that look like in terms of using this? What are these parameters? So in this case, I'm just looking at a very simple Langevin particle and computing the velocity autocorrelation across time on the X, and that's the correlation on the Z axis across different parameters. So as we increase the blocks and the points, this effectively extends how many lags we have access to and our resolution, especially with the points. And the averaging, we can see we can extend to much longer timescales, but we have a much coarser picture of the correlation function. Okay. So coming back to DL Poly on this, how we implemented this from a software design perspective is, so we have this, we have a correlator, so that's the multi-tau algorithm, which accepts some data and correlates it. And what the pattern we followed is we wanted to kernelize the X and Y, these observables, because what we want is, instead of having to re-implement or tinker around with our main simulation loop, if we want to add new correlations, new observables, we want to have some abstract way of getting these values, because we can do that. So we can we define a correlation algorithm which correlates data, and then if we want to support new correlations, we have getters which take the data in and pass it to the algorithm. So yes, we have these two paradigms of kernelizing, but also separation of concerns, where we have the correlation algorithm which just correlates the data and doesn't really care what it is, and the rest of the code which selects the observables. So quickly from a user point of view, what that looks like is we have input and output files, so you don't necessarily need to read the details here, but the idea is we have some input where we can select correlation. So in this case, stress, velocity, or heat flux, or whatever you want. Choose your parameters, and then get the output in the output file. Again, you don't need to look into the details very much more than that. There's in an output file, we have the correlations listed out as different lag times and also derived data. So these are our system properties. For example, in this case, I think I've got viscosity and kinematic viscosity up here, just as two examples from the stress autocorrelation function there. So obviously it's all well and good, but how do we verify that this is actually proceeding and working as expected? So this is a very simple little case study using Argon. And why are we using Argon? Because there's some nice NIST data, experimental data for certain properties, in particular viscosity. And there's a simple Lennard-Jones model, which is known to capture these. You can find in these references down here. So, and obviously we get kind of the expected results if our implementation was working, which it is. On the left here, we have the heat flux, and on the right, we have the viscosity at different temperatures in the Argon system. So just a word on the reproducibility of that. So the workflow we have, so this is, again, the details don't necessarily matter, but we have a Python script where we can encode what our workflow is, moving different temperatures, different seeds, loading the correlations and the derived data, all from DL Poly, rather than having to interact with the executable itself. But this example of the stress autocorrelation function, for example, and the heat flux is not very intensive in terms of data storage. So because stress, for example, is just some small amount of data, you take it every time step. We're not saving the configuration there, we don't need it. A more interesting example to compare for our code is the velocity autocorrelation function, where you will need, for example, atom velocities to be able to work this out. Now, on the left here, I have a comparison of calculating the VAF after the simulation is run. So we store the trajectory and then calculate the VAF compared to the online, which obviously doesn't store data except for the initial configuration. That's in terms of disk usage, and on the right in terms of runtime. To essentially look at what our potential runtime impact is of the online calculation. And I've also put an example in yellow of a simple Python script to do the post-processing, which is not the most efficient way of doing it. But the take-home really is that we eliminate the storage, trajectory storage, and we're able to calculate the VAF with very little overhead. So yeah, and that brings me on to the conclusions. So we've successfully managed to implement a general framework for on-the-fly correlation functions in DL Poly with little overhead and an improvement, for example, in over trajectory storage in cases like the VAF, and a proof of concept for more system properties and other things that we can implement in DL Poly using this methodology. So with that, I'd just like to acknowledge the various team of people who worked on DL Poly and also at Queen Mary, the various HPC platforms I've been using, and our funders. And yeah, thank you very much.